In this video, we are going to take a look at an introduction to graphing rational functions. So a rational function is just going to be a function that has division in it. So you're going to have some polynomial function in the numerator and some polynomial function in the denominator. And remember that we can't do division by 0 ever in math. So the denominator of this cannot equal 0. And that's going to be your issues with your domain. So your domain is going to be all real numbers except any of the numbers that make the denominator 0. So let's take a look at this example and go ahead and find the domain. So we want to figure out where this denominator equals 0. Those are going to be our bad values. So we're going to look at x squared minus 3x plus 2 when that equals 0. So we'll want to factor this. And so when we factor this, we've got a positive 2. Okay, so multiply to positive 2, add to negative 3. So that's going to be negative 2 and negative 1. Anytime two numbers multiply to equal 0, we know that we can get 0 when either of those factors or any of the factors are equal to 0. So then we'll split it, set it equal to 0, and solve. So we'll add 2 to both sides, and here we'll add 1 to both sides. So these are our bad domain values. So one way to say the domain would be to write out all real numbers except, let me fix that. Okay, so all real numbers except 1 and 2. If you're going to write it out in interval notation, one thing I like to look at is looking at it as looking at the whole number line of x values. So we have negative infinity to infinity, so that would be all real numbers. And in this case, our problem values are 1 and 2. So we do not want those. So these are going to be bad, but everything here is good. Everything here is good. And everything here is good. So we'll just name those intervals. So negative infinity all the way up to 1 is good. Remember, 1 is not good, so we'll just put a soft bracket. Then we're going to restart again right above 1, so a soft bracket until 2. Soft bracket since 2 is not included. And then we'll start again at 2, right after 2, up until infinity. So this would be the interval notation of all real numbers except 1 and 2. All right, so let's look at vertical asymptotes. So for vertical asymptotes, this is the generic form of a vertical asymptote. So we do limit notation as x approaches the vertical asymptote. So A just represents whatever the vertical asymptote is from the left. So when you have this negative up here in the exponent, that means when we're looking at it from coming in from the left side. And then this is as x approaches the vertical asymptote from the right side. Now a vertical asymptote is either, the function is either going to be going to positive infinity or negative infinity. Okay, those are the only options for vertical asymptotes. So let's take a look at this specific example. So in this specific example, okay, our vertical asymptote is at negative 3. So the limit as x approaches negative 3 from the left, okay, and that's coming at it from this side. So you could think about like if you just, covered up this side. So if I just covered up part of the graph. So if we're looking at it from the left side, okay, where is the graph going? And this graph is going up on the left side of the asymptote, so at positive infinity. Then this one, we're looking at as x approaches negative 3 from the right side. So this one, we're looking over here. Okay, and when we look on this side, where is that graph going? So on the right side of the asymptote, it's down at negative infinity. For horizontal asymptotes, sometimes these are called end behavior asymptotes because it's what your graph is doing at either end of the graph. So on the very left side of the graph or on the very right side of the graph. And so this one we look at as x approaches infinity, which is the very right-hand side of the graph. So the really, really, really big x values. Okay. Or we look at as x goes to negative infinity, the left side of the graph. Okay. So the very right side of the graph and really the right end. Okay. And the left end of the graph. Okay. So as far as you could go to the left possible. So now these are going to approach the actual horizontal asymptote value. So you can see that these are just getting closer and closer to this green line as we go out on the ends. So for this case specifically, this is a horizontal asymptote of y equals 2. So as x approaches infinity, we can see that our graph is just getting closer and closer to that y value of 2. And as we go towards negative infinity x values, again, the graph is just going towards 2. So when we go to find holes and vertical asymptotes, so we talked about vertical asymptotes, they're bad values of the domain. There's also a potential for holes. Both of these occur when the denominator equals 0. And then we also have some x-intercepts that we're going to talk about in this too. So here's kind of the steps to finding holes, vertical asymptotes, and x-intercepts. So first thing we're going to do is simplify the rational function by factoring both the top and bottom. Then you're going to find the zeros of both the top and bottom. Now, any zeros that are in common with both are going to give you a hole. Any that are only in the denominator are going to give you a vertical asymptote. And any that are only in the top are going to be an x-intercept. Okay, so factor top and bottom, find the zeros. Then we're going to see if they're common to both or unique to one. So in this example, so again, we'll factor both the top and bottom. Okay, so we're going to start by factoring. So this top has an x in common. So we're going to factor it out, and then we're going to be left with x minus 3. The bottom has a 3x in common. And when we factor that out, we're going to be left with x plus 2. So now we're going to find the zeros of both the top and bottom, so where they equal 0. So that means that each factor is going to equal 0. So x equals 0 and x minus 3 equals 0 for the top. So we'll add 3 to both sides. So there's my 2 zeros for the top. Then we'll do the same thing on the bottom. So 3x equals 0 and x plus 2 equals 0. Divide by 3 and you get a x equals 0. Subtract 2 and you get x equals negative 2. So now we're going to go ahead and look, okay, about if they're in common or not. So remember, for a whole, they're going to be in common. So we're going to see the same 0 on top and bottom. So we see that x equals 0 is a 0 on both the top and bottom. So we have a whole at x equals 0. Now this is going to be an ordered pair, so we actually need to plug 0 in, okay, but you're going to plug it in after you get rid of this factor, okay, the common factor, and actually just this common x. So now you'll plug it into this function, okay, so you'll plug 0 in. So we have 0 minus 3 is negative 3. 0 plus 2 is 2, so we have negative 3 on top, and then 2 times 3 on bottom. So then we get a whole of negative 1/2, 0, negative 1/2. So then for our vertical asymptotes, okay, our vertical asymptotes are unique or only in the bottom. Okay, so these are only in the bottom. So then we're going to look at this 0 in the bottom of negative 2. That is not in the top, so that's our vertical asymptote. Now, a vertical asymptote is an equation, so it's the equation x equals negative 2. Then our x-intercepts are only in the top. Okay, so then we see that this x equals 3 is only in the top. So our x-intercept is the 0.30, because remember, that's going to be where it crosses the x-axis, okay, at x equals 3. So this ordered pair would be an x value, and then the y value is going to be 0. All right, then when we think about end behavior asymptotes, so end behavior asymptotes have to deal with the degree of the numerator, okay, and the degree of the denominator. So we're going to be comparing these. So if the degree on top is smaller than the bottom, then your horizontal asymptote is automatically y equals 0. So if you had something like 3x to the second over 2x to the fifth, automatically y equals 0 because 2 is less than 5. If the degrees are the same, so if they are equal to each other, then we divide these lead coefficients. Okay, so then it's y equals a over b. So if we had 3x to the fourth over 5x to the fourth, and you could have other stuff here. This one, the horizontal asymptote would be y equals 3/5. So just dividing those lead coefficients. And then if your numerator degree is bigger than your denominator degree, then there is no horizontal asymptote. We are going to get a slant asymptote, which we'll talk about later, how to find that, but there's going to be no horizontal asymptote. Okay, so if you had something like 3x to the fourth over 5x squared, okay, and again, you can have more stuff, we just care about the lead term, then this one would have no horizontal asymptote.